So, hello everyone, my name is Anat, and I'm going to talk about polynomial secret sharing schemes, and this is a joint work with Artiom and Radune, my former student who has graduated by now. Okay, so let us have a quick recap of what secret sharing schemes are. You've probably heard enough about the setting in this session, but let's have a quick recap. So a secret sharing scheme is a randomized mapping taking a secret that comes from some finite domain S, and the randomness that is uniformly sampled from a finite domain R, and outputs shares, n shares, to n parties. So the ice party gets the ice share, and the goal is that some subsets are able to recover the secret from their share, while other subsets don't learn anything. So this setting was introduced by Shamir and Blakely in the late 70s for the threshold case, where basically large subsets can recover and small subsets can't. For instance, all those of having over a third of all parties can recover, while the rest can't. And their scheme, the Shamir scheme, for instance, works for is a family of schemes actually that works for all. So one scheme for each threshold. And a few years later, secret sharing schemes were designed for any monotone access structure. That is, it is unavoidable that if a set can recover the secret, then any superset can recover the secret, but otherwise the access structures are arbitrary. So every access structure has a secret sharing scheme. To clarify our setting slightly further, we mean that we have perfect correctness, so that so-called authorized sets that can recover the secret with probability 1 over the choice of their randomness, while unauthorized sets see exactly the same distribution for any shared secret, so they get no advantage at learning the secret whatsoever from their shares. And I want to stress that we focus on the standard setting of perfect secret sharing with perfect privacy and perfect correctness, as we just defined. So, for example, in Shamir's scheme, the secrets come from a finite field, some FQ, and the randomness domain is a set of vectors of lengths n minus 1, and each party gets an evaluation of a polynomial at a certain point associated with it, and the polynomial has S as its free coefficient, and the randomness vector as the rest of its coefficients. It's a degree n minus 1 polynomial. Okay, a very popular set of secret sharing schemes are linear secret sharing schemes, where each share consists of linear combinations, one or more, of the secret, which is a single field element over some finite field. And the randomness elements, there are some k elements, which are also elements of the same field. Yeah, so we can write it this way. And this type of schemes has found many applications, for instance, beyond storage, like in MPC, for instance, and even designing MPC for general adversarial structures, and many more. So, for instance, one nice property such schemes have is additive homomorphism, right? Where if you locally add shares, each party locally adds its shares, they get sharing of the sum of the secrets, which is nice. And this, so in Karchmer and Wigderson in '93 defined a complexity theoretic model based on some linear algebra, which is equivalent to such linear secret sharing schemes called monotone span programs, and studied it. They were the first to study it, and several subsequent works continued to study it. But one thing that is not hard to see is that any access structure viewed as a monotone function that can be implemented by a polynomial-sized MSP is contained in NC. So it's not, it can't be very complicated, just by observing how the secrets can be encoded and recovered in NC, because basically it's based on linear algebra. So arguably the most important measure in secret sharing schemes is their share complexity. So what is the share complexity of a secret sharing scheme? It's basically the total number of bits in the longest share received by everyone together. Sometimes it's defined as the maximum length of a single share, but we will usually consider the hardest schemes, which are at least currently, which they have exponential share complexity, so we don't mind the n factor, the polynomial factor, which is the difference between the two definitions. Similarly, one can consider the information rate of a sharing scheme, which is the same as the share complexity, but normalized by the secret length. Right? So sometimes one could think that if we share longer secrets, we can get a better overhead per secret bit. And sometimes it suffices even if we have very long secrets. Okay, so what is the state of the art in terms of positive and negative results? So we have mentioned that in the 80s already, it was shown that all secret sharing schemes, all monotone access structures have secret sharing schemes. And actually, these schemes were linear. Actually, most schemes constructed so far were linear secret sharing schemes, also both because of their advantages we discussed and because they're possibly easier to design. And until the previous schemes were basically were based on monotone formula size and things like that. So they were some of size order 2 to the n. And in a recent breakthrough of Liu et al., it has been shown that this is actually not necessary. So we can even beat even non-monotone circuit size, which was surprising. And it attracted that result going below 2 to the n, minus some small factors here in the exponent, attracted renewed interest in this area. And recently, Applebaum et al. Are the record holders for share complexity of general secret sharing schemes with 2 to the point 64 n. And for linear schemes, the best known result is also theirs, slightly worse. It's 2 to the point 76 n. On the other hand, on the lower bound front, we know much less. So there's this huge gap. For general secret sharing schemes, the best lower bound is about n squared total size, not even. And on the other hand, for linear, there are much better bounds, which are basically exponential bounds. And here, let me stress 2 things. So first, the lower bounds are for the information rate, so they're actually even stronger. And also note that for linear schemes, for a fixed field, say let's treat the field size as a constant, one could get an existential 2 to the omega n lower bound just by counting. Basically, they're counting all possible schemes with a certain share complexity. So that was known for a long time, and quite surprisingly, these bounds hold for all linear secret sharing schemes. That is, there are access structures which require that kind of rate for any linear scheme for arbitrary fields, no matter how large. There are quite interesting techniques involved here. On the other hand, for general secret sharing schemes, because we basically don't assume anything about the complexity of the computational complexity or any kind of model for the encoding and the decoding algorithms, counting wouldn't work. So this bound is actually for an explicit text structure, but we don't know any better for even existentially. So there's a double exponential number generally of schemes. Okay, so it seems hard to beat that. And indeed, the best bound is by Xirmaz from 94. Multilinear schemes are similar to linear schemes, with the only difference that the secret is some vector of length m over the field rather than a single field element. So these were also studied quite a bit, but somewhat less, quite a big deal, quite a lot less than linear schemes, because, for instance, in some applications, it's unclear how to replace a linear scheme by a multilinear scheme. For instance, for the application of devising a MPC for general adversary structures. And the advantage of considering multilinear schemes over linear schemes is gaining on the information rate, right? So possibly we could have longer secrets for this same shear complexity. And there are some results showing that for some access structures, this is indeed the case. Okay, so for multilinear schemes, the upper bound is still exponential, while the lower bounds are less good than for linear, but still much better than for general schemes. So again, the structure, the algebraic structure, basically in multilinear schemes, helps with lower bounds. Okay, so in this work, we introduce a model that naturally generalizes multilinear schemes into polynomial schemes of higher degree, possibly higher degree. Right, so in our setting, the secret comes from a domain of vectors of length k over a finite field, and the randomness is also of that form, of some other vector lengths. And every shear consists of one or more multilinear polynomials in the SIs and the RIs. So for instance, the multilinear schemes, which we abbreviate as ML, are captured by a degree 1 here. And the linear scheme, in the linear schemes, we additionally restrict k to be 1. Right? And here we denote the set of polynomials where the secret and the randomness are of a certain degree, where this star stands for an arbitrary non-negative degree. Right, so it stands for all these polynomials. So for instance, here we have polynomials of degree exactly 1 in R and arbitrary degree in S, plus polynomials of degree 0 in R and degree and arbitrary degree in S. Okay, so why do we introduce this model? So basically, in this work, we just initiate the systematic study of this model. So a few works from the literature already fall into this framework, but there is still quite a lot that is not known. And our main goal, is the hope that it will help obtain lower bounds for a broader class than multilinear schemes, for instance. So they're more powerful, right, than linear schemes, the multilinear, but because they have somewhat less structure, it's harder to prove lower bounds for them, right? There is some trade-off. But still, they're much better lower bounds than for general. So we introduced some kind of intermediate model where we hoped to still retain enough structure to be able to prove lower bounds, and on the other hand, we hope it's powerful enough and goes a step closer to general schemes. So for instance, what can we say for degree 2? Okay, so that's our main motivation. Also note that without the degree restriction, polynomial schemes are basically they capture almost all secret sharing schemes without a change, basically. So we can take any scheme and just represent it as a polynomial scheme, almost. So we will talk about it again in the future work. And the secondary motivation is to maybe obtain better constructions for various access structures. So while possibly less easy than designing linear schemes or multilinear schemes, there's hopefully enough structure to still be able to understand how to do things and to get better results. And there is, as we'll see, some evidence that sometimes it is indeed the case. Okay, so let me quickly mention some of our results. So on the negative side, we prove that degree 1 in R almost doesn't help over multilinear schemes. So what do I mean by that? There is a large subclass of degree 1 in R polynomial schemes, which is a superclass of the strict superclass of the multilinear schemes, that are not stronger than multilinear in the sense that every secret sharing scheme of this type has an equivalent multilinear scheme with shear complexity, which is very similar. So here it's actually the same, and here the overhead is some polynomial factor. Another thing we show is that for degree 2, we must have linear monomials in R present, or else the scheme becomes very weak, and not only in even in the sense of having large shares, but also it is only able to implement some very simple access structures, namely those where basically each party either gets the secret or not. So the min terms are singletons in these schemes. And this result is maybe not very surprising, but it's non-trivial, and it relies on some understanding of the structure of quadratic forms. Okay, so these are our negative results. Okay, another measure that we consider is the randomness complexity of secret sharing schemes. So what is the randomness complexity? It's basically the length in bits of the randomness received by the sharing algorithm. Okay, so why is it interesting? Let me try to convince you that it's interesting. So one thing for which a low randomness complexity would be interesting is obtaining counting-based lower bounds. So for some, say, m input variables, polynomials over some fixed finite field, there are quite few of them, right? So we could have pretty good lower bounds in case the randomness, which is part of the input to these share polynomials, could be upper bounded as a function of the share complexity. In particular, if we could have this kind of okay, and the bounds are good basically if the degree is low, right? So for arbitrary degree, we almost don't gain anything over non-polynomial secret sharing schemes, but let's say for degree 2 even, which we already don't understand well, we could get better just counting-based bounds. But if the randomness vector is very long, we don't get it. So it's not hard to see that if we had this kind of exponential but not very large bound of randomness complexity as a function of the share complexity, we would already beat the lower bounds for not the information rate, but the share complexity at least, for general secret sharing schemes. Another nice application for good randomness complexity would be showing that degree 3 is quite powerful. In particular, every constant degree PSSS would have an equivalent degree 3, total degree, here it's speak about total degree, PSSS, with share complexity that is only polynomial in the share complexity of the original scheme. And this observation is based on some constructions from the literature of randomizing polynomials for algebraic branching programs. So over rings, actually even more general structures. So basically this is because polynomials can be modeled as for algebraic formulas which have small algebraic branching programs in turn. So our positive results make a step in this direction of upper bounding the randomness complexity, in particular for the class of, for the kind of minimal class of degree 2 schemes, we get an exponential upper bound. So the concrete polynomial here is about quadratic, which is still not sufficient for existential lower bounds on the share complexity, which are interesting, but it's a step in this direction. Another result we get is a similar upper bound on the randomness complexity for general polynomial secret sharing schemes. And along the way, we get similar results for just general schemes. So to clarify, if we were talking about statistical schemes, then the bound for general schemes would be trivial. But because we're interested in perfect privacy and correctness, this is not the case. Okay, so we would, in the deep dive, we will provide the proof for the for Theorem 1.1, showing that for degree 1 in R, where the monomials free of R's are degree 1 in S, are equivalent to multilinear in the sense that there exists for every such scheme, there exists a multilinear scheme with the same share complexity, actually. The proof is pretty short and easy, and it's actually quite surprising. So let me just mention the proof idea, and we will provide the quite short proof in the deep dive. So it turns out that substituting S for S1 in some fixed value in all monomials, in all coefficients of the randomness, not in the wherever S appears by itself, but wherever it's a coefficient of R, suffices to obtain a scheme that is a secret share scheme for the same access structure, and clearly it has the same share complexity. So if we look here, we basically just substitute S1 in this matrix, and it turns out that it works. So the scheme is clearly multilinear, and it works. And in the deep dive part, we will provide the proof, which is pretty simple. Let me skip it for now. Directly to future work. So we have defined a new framework of polynomial secret sharing schemes, and have obtained some preliminary results, but there are many more questions to explore, and hopefully they will be useful for understanding, as a step for understanding general secret sharing schemes better. So one fundamental question that is open is whether general schemes are more powerful than polynomial schemes. And some evidence to that are some secret sharing schemes from the literature based on matching vector families. So small matching vector families yield basically good secret sharing schemes in a way, in some constructions. And these families have to work over rings which are not fields. So also here I want to stress why polynomial schemes are not equivalent to general schemes in terms of having the same share complexity with no change. So think about a scheme where R is of size 6, for instance. So there is some probability of a certain share vector that can be 1/6, let's say. And that's not a multiple of any negative power of a prime, which is what you would get in any PSSS. Okay. Another question is, can we show that degree 2, for instance, is more powerful than degree 1? So for k equals 1 and for some fields, separation is known. But it's not clear what happens for larger values of k. In particular, there are some results from the literature showing that multilinear schemes can be super polynomially stronger in terms of share complexity than linear schemes when we look at information rate. So that's an interesting open question. Another open question is to improve the upper bounds we obtained on the randomness complexity for low degree schemes, which in particular would yield the non-trivial lower bounds on share complexity for fixed fields. And there are some other questions of investigating other parameters that fall in this framework, like the effect a particular field has on the share complexity of the resulting schemes. And there are some results in the literature in this direction as well. So about linear schemes. So what can we say about k equals 1 and d equals 2, for instance? Okay, so thank you very much. And whoever still has patience, let us move on to the deep dive. Thank you. Okay, so welcome to the deep dive part of this presentation. And I'll show you two proofs. One of Theorem 1.1. So as a part of the result showing that degree 1 in R is not very powerful. It's basically as powerful as multilinear in terms of share complexity. And next I will show you, I'll give you some idea on the proof techniques on the upper bound on the randomness of general polynomial secret sharing schemes. And I'll only mention that the upper bound on the randomness for degree 2 use quite different techniques and heavily rely on the structure, the algebraic structure of degree 2 polynomials, and you're welcome to read the paper to see how it works. Okay, but let's start with this proof, which is really surprisingly simple. So as we mentioned, what we do is consider some scheme of this type. And so it's represented by a pair of matrices, one multiplying the secret vectors and one multiplying the randomness vector. And this ms multiplying the randomness vector depends on s. And it turns out that if we replace the formal variable s by substituting some particular value s1, we will again obtain valid perfect secret sharing scheme for the same access structure, and it will be a multilinear. Okay, so let's see how that goes. So let us fix some value of the secret, some vector. Let's call it S1. So correctness is equivalent to saying that for every okay, it's not equivalent. It implies, because S1 is fixed, but it implies the following: correctness of the original scheme implies that for every S0 that we substitute here, and for every choice of randomness R1 and R0, the resulting sharings that we get for some authorized set in both cases will differ. And why is that? Because the output distributions corresponding to different secrets should be disjoint for authorized sets to get perfect correctness. So here we use perfect correctness. Now let us do the following trick. So if the previous thing holds, so in particular it holds for R0, which is the zero vector. So substituting that, we get this inequality for every S0. Now, because it's for every S0, then for every single secret vector, we can match an S1 such that this difference equals this vector, Sj. And again, because this R1 was arbitrary, we can substitute any difference of two randomness vectors to get some R1. And here, because that value that was previously a difference is again arbitrary for that fixed S1, because we can play with S0, this difference we can now replace it by this vector. We can write it as the difference of any pair of secrets. Right? Now, rearranging, we obtain this inequality for every pair of secrets S2 and S3, and every choice of randomness here and here. So note that this is a sharing of S2 according to the new scheme, and this is a sharing of S3 according to the new scheme, and this is exactly equivalent to the new scheme satisfying perfect correctness. Okay, let us move on to privacy. So privacy tells us that for any unauthorized set of parties, the output distributions of the shares that are seen for different secrets are the same. In particular, that implies that for that S1, note it's the same S1, and any S0, and any choice of R1, let's do it the other way. Every choice of this Rj, we have a choice of R1 such that this equality holds, right? Because if the distributions are the same, in particular, they have the same support. Okay, so again, let us substitute 0 for Rj. Okay, so we get this equality. So note that this R1 may depend on S0, and it's just guaranteed to exist. It's not an arbitrary R1, not any R1 as for the correctness. But still, since it works for every S0, we can obtain any vector here for the same R1, depending on what the original S0 was. So again, R1 depends on this vector, but this is fine. Now, since we can get any vector here, it can be the difference of any pair of share vectors, right? And on this side, this R1 depends on this pair of vectors, so think of it as fixed. But now it can be represented as the difference of two vectors, one of which can change freely, and the other one is a corresponding vector. Rearranging, we get this equality. So this so here, as opposed to correctness, we're not done yet. This just shows that for every R2 and every secret S2, there is a value in the sharing of S3. So this is again the expression for the sharing of this secret in the new scheme. So there is a corresponding value in the support of the sharing of any other secret. So for any pair of secrets, this exists. And now we should additionally use the fact that this is actually a coset of some linear subspace to to infer that this equality of supports actually implies an equality of the distributions, of the output distributions for the unauthorized sets. Yeah, but basically it is pretty simple. Okay, so the last thing I will show you is the proof sketch of this theorem 4, saying that if you have a general secret sharing scheme, actually, then you can have always devise an equivalent secret sharing scheme, most perfect, where the randomness complexity is at most exponential in the share complexity. And by default, no bounds were known, again, as far as I know, even for the general case of no restrictions. And furthermore, if it's polynomial, then the resulting scheme is also polynomial, albeit it can have a higher degree. So let us start with a proof sketch for theorem 4. So we start with some general secret sharing scheme, not necessarily a polynomial one, for some monotone X structure. And we want to devise an equivalent secret sharing scheme for the same X structure, also with exactly the same share complexity. Actually, we'll have the same secret and share domains, but hopefully with sufficiently small randomness as a function of the size of this share domain. Okay, so what do we do? So we notice that we can restate the existence of such a secret sharing scheme with this complexity for this X structure as the existence of a certain vector of probabilities. So for every, basically this mapping induces for every secret and every share vector in this S1 times Sn induces some probability of outputting this vector V on an input S by this or any sharing algorithm that will work. So what would we require from these probabilities? So for once, we want the PSVs to be non-negative because these are probabilities. And also, we want that for every secret, indeed, the PSV, the vector PS something of with the various V's is a probability distribution. So it would require that the sum over all V's of PSV is exactly 1. So we have this constraint that we have valid probability distributions. And then we need to devise constraints for the privacy and correctness of the scheme relatively to this A. So privacy is rather simple. What we require is that the output distributions seen by any max term A, and for any pair of secrets S and S prime, the probability distributions seen by A from its shares are the same. So in particular, so this is equivalent to saying that for every UA, which is a value of the share vector seen by A, we have that the probability of seeing UA is the same in both cases. So we can restate it as having the sum over all V's such that VA equals UA of PSV, which is exactly the probability of hitting UA with the vector S, equals this probability. So this is a privacy constraint. Now for correctness, what we require is that for every min term, the share distributions seen by A for different secrets are completely disjoint, right? In other words, for every such UA, at most one of the probabilities of seeing UA for S and S prime are 0. Is non-zero. So the other has to be 0. Actually, exactly one of them, of all secrets can at most have non-zero probability, and the rest have 0 probabilities. And of course, for some UAs, we can have just 0 probabilities all over for all secrets. So what we might want to require is that at most one of them is 0. In other words, the product of the corresponding probabilities. Right here we have S, and here we have S prime. So the same expression as here is 0. right? But that would give us a degree 2 constraint, which is more complicated to deal with, so we don't want that. So here's a trick. Here's how we can simplify matters. Let us not just require correctness for A, but let's recall that this sharing scheme is a valid solution to this correctness set of constraints and also all other constraints. So that's a valid solution. So let's require that any solution we are looking for to look like this solution, right? And now, okay, I forgot to mention, whenever we actually get, maybe I forgot, I don't remember, a solution with these probabilities being rational, then we can go back and have a sharing scheme, right? Replace it with a sharing scheme. So that's what we hope to do, and indeed we will end up having some rational solutions to this set of constraints. But anyway, let's get back to this sharing scheme. So this sharing scheme, it has already determined for each values of S for a given UA, which values of S are have a 0 probability of hitting UA, and which have a probability of a non-zero probability, and some possibly have all secrets yielding 0 probabilities. So what we do is we go over for every A and every UA, for all S values that yield a 0, let's require a 0 here, a 0 probability, right? So for UA, for instance, all but all S which are not some S2 have zeros, then let us require that PSV for all V's such that VA equals UA is 0, right? So we'll have such a constraint for every S which is not S2. Great. So now we are sure there is a solution, and we have gotten a linear program in a canonical form of the following structure. So we have some matrix A times our vector P equals a vector B, right? Where these are the probability constraints, and these are the correctness, the randomness, the privacy and the correctness constraints, where here we have ones, and we have zeros for the rest. And also in A is just a matrix of zeros and ones, because that's what we got in our with our constraints. Great. So let's somewhat analyze the size of this A. So A has roughly 2 to the n times 2 to the share complexity, which is just the share domain size constraints. Why is that? So roughly for every min term and every max term, we okay, let's say poly. We don't want to make precise calculations. Right, so for every min term and every max term, we have some set of constraints, so they're like 2 to the n of these. And now for each, we go over all the UA values, so there are at most as many as 2 to the share complexity of these, right? And also for every secret, we have something where the secret domain is at least as is upper bounded by the share size domain, so we get something like that. Right, that's overall it's 2 to the poly share complexity. Well, it's not very large. And now by some theory of by basic theory of linear programs, it is known that any bounded any linear program with a bounded feasible region, like in our case, because all the probabilities sit in the 0-1 area, it has at least one basic feasible solution of the following form. So let us take some submatrix of A, which is non-singular, square and non-singular, and the corresponding solution, the basic feasible solution, has possibly non-zeros in the entries corresponding to the columns of this A tilde, let's call it, and zeros elsewhere. So this basic feasible solution satisfies something like A tilde times this P tilde, let's call this region, equals B. So P tilde is A tilde inverse times B. Nice. So because this A matrix is A tilde matrix is a 0-1 matrix, and so is the B, by some simple calculations, by a formula for Cramer's rule for the inverse of a matrix, we deduce that every entry in this A tilde in this inverse matrix is a multiple of some 1 over m, where m is not extremely large. So let's make a quick calculation how large that m is, and m is an integer. Okay, so how can we bound this m? For an n over n matrix of zeros and ones, this m is about something like n to the n. So it's upper bounded by something like that. So it's 2 to the n log n, right? So in our case, this n is something like 2 to the poly share complexity, polynomial of the share complexity. So it's something like 2 to the 2 to the polynomial in the share complexity. So this m is pretty large, but it's not that horrible, right? It is horrible, but it's a start. Okay, so what can we do with this m? So because so that's the case with A, and also this will also be the case with P tilde. So all entries in P tilde are multiples of this 1 over m. So now we can take R just to be m, and we're guaranteed to be able to set up some mapping, which, substituting this R here, which agrees with this BFS solution, and this will induce our share prime. So even if we started here with randomness complexity, which is like 2 to the 2, 2 to the 2 to the n, like really, really large, here the randomness domain is just that large, and the randomness complexity is the log of that, right? So now it looks less scary. So it's something like 2 to the polynomial in the share complexity, as we claimed, and if we make the precise calculations, we get what is said in the theorem. Okay, good. So that was a kind of a proof sketch for a general secret sharing scheme. Now, how do we, if the sharing scheme was initially a polynomial secret sharing scheme over some field FQ, how do we make sure that the new scheme is also a polynomial scheme over FQ? So it suffices that the m from before is a multiple of q to the minus t prime for some integer t prime, right? And then we can have t prime elements in the randomness vector. And so we want to prove that there exists such a solution where this t prime is not too large, and also indeed this m has this form. So what, on a high level, what we do is finding such an m in this feasible region, which will not necessarily be a BFS as before, but using the fact that there exists some solution, basically one corresponding to the original sharing scheme, where all entries are multiples of q to the minus t for some t, possibly extremely large, like the one we showed before, or even larger, right? We didn't have any a priori bound. So there also exists some other solution where the entries are both multiples of this power of q, and this power is not too large. Okay, so this is all I had to say today. Thanks a lot for listening, and you can read the full version on ePrint for more details.